Hello, hello. No, it's working. Okay. Oh, we're recording. Good. All right. So if you looked at the test for review, which hopefully you did, it's primarily hypothesis testing. Now, I told you to identify the test statistic, sketch the curve, identify the critical values, and calculate the p-value for all of them. On the test, you won't have to do it for all of them, but you will have to give me each of these things at least once. Again, it'll just be random. On the test, there could be one Z, there could be three Z's, there could be one T, there could be three T's, four total. Right here, if we look at it, let's see what we got. It says the CEO of a company, and who cares, has a mean work, continue recording. Well, hopefully the audio records saying it might not, whatever. That the mean work day of the company's mechanical engineer is less than 9.3 hours. A random sample of 27 of the company's mechanical engineers has a mean work day of 8.6 hours. The population standard deviation is known to be 1.21. There's my alpha. So let's start with our null alternative hypotheses. H0, H1. So let's see what we got going on. It says that the CEO is claiming that it's less than 9.3. Less than doesn't have equality in it, so it's going into the alternative. That makes our null greater than or equal to 9.3. All right, let's write down the rest of the information. A random sample of 27, so N is 27, has a mean work day of 8.6. So that's a sample having a mean of 8.6. That's our X bar. The population standard deviation. Well, that tells us what we're dealing with here. Remember, population standard deviation is sigma. And if we know sigma, we know it's a Z test. So this indicates that we have a Z going on. Our alpha value is 0.02. And we're going to test the CEO's claim that it's less than 9.3. That's my claim. And it's assuming the population is only distributed again. Don't worry about the conditions. They will be met. And if they're not met, assume they're met, because I'm not going to make you not do the problems. So let's see what we got going on here. We need to calculate the test statistic. So let's find that first. It's a Z, so we're going to get the Z test statistic. If you don't remember, it's on your formula sheet. Got a bunch of algebra 2 right now. Hang on. It's on your formula sheet. Right here, chapter 8, test statistics. We have a proportion for the mean. Mean has two, one's a Z, one's a T. We're dealing with the Z right here. And again, this is a Z score. Where's my mouse? Oops. There's my mouse. So again, this is a Z score. This is a Z score. Your critical values are Z scores. They're all Z scores. So be specific. This is your test statistic. So don't call it the Z score because there's more than one. The test statistic has this formula here. Any day now. There it is. That's the formula. So plug in the information and see what the test statistic is. X bar is 8.6 minus mu is 9.3 over sigma is 1.21 divided by square root of n. N is 27. So I'll do this on the Casio. TI users, you can just type this information in and be done with it. Casio users, you have to do slightly more work. Make sure in mode 1. We got a fraction, 8.6 minus 9.3. In the denominator, we have another fraction, 1.21 over square root of 27. So negative 3.0060. I'm going to go 4 decimal places to be safe. Negative 3.0060. That's my test statistic. Notice it's a left tail. So whenever we get our critical value, which is going to be next, we're going to sketch the curve and plot the critical value. We need to make sure we get the negative one. If the left tail is negative, the right tail is positive. Two tails both. And you have to split alpha in half. We have a left tail, so we're going to use 0.02 as our alpha. So on the chart, we're looking for 0.02, not 0.02, should be somewhere around here. Here's 0.0202, here's 0.0197. This is 3 away, that's 2 away, this one's closer, so that's what I'm going to use. That's going to end in a 5. That's going to be negative 2.05, negative 2.05. So my critical value is 2.05. It's a left tail, so I'm going to make that negative. Now we got to sketch this curve. So I'll do that here. There's my normal curve. Means in the middle, it's always 0 for the standard normal distribution. We've got a critical value of negative 2.05. So I'll put that right here. Negative 2.05. There's a decimal there. And in red, I'll put my test statistic. So the critical region is to the left because it's a left tail. I'll shade that way. And my test statistic is in that critical region. Right there is the negative 3.01. I'll round it to 3 decimals or 2 decimals. Since the critical or the test statistic is in the critical region, we reject the null. That is, where is that? That is, well, this part, write the initial conclusion for the null. We're going to reject the null. Now we also need to get the p-value from this thing. So I'm going to go to our chart, our finding p-values flow chart. What kind of tail do we have? Left-tailed. Find the area to the left of the test statistic. Easy enough. So the test statistic is negative 3.01 if we round to 2 decimal places. Oops. So I'm going to go find the area of that, negative 3.01 right here. So my p-value is 0.0013. So my p-value is 0.0013. And we can also say p is less than alpha. And if that's the case, we reject the null. So either way we do the test, either the traditional method or the p-value method, both result in rejection of the null, which they better match, otherwise you did something wrong. Oh, we lost somebody. Oh well. So the last thing is to write the final conclusion. So anybody trying to come in? Yep. So we rejected the null. The claim is in the alternative. So there is enough evidence to support the, oh, I got a question. Audio is not working. Oh wait, who's got a question? I'll be right back. I have to meet with my advisor at 1:30. Okay. Okay, see you when I see you. There's enough evidence to support the claim that And let's see what the claim was. The mean workday of a company's mechanical engineer is less than 9.3 hours. Oops. The mean workday of the company's mechanical engineer is less than 9.3 hours. And that's it. So if you do have a TI, all you need to do would be to type in this information into your Z test. So TI users, here you go. I won't do this every time, but I'll do it this time. Stat test, this is Z test. We've got stats. Mu is 9.3. Sigma is 1.21. X bar is 8.6. N is 27. It's a left tail. And we calculate. It gives us our test statistic and our p-value instantly. You still need to find the critical values because it tells you to. And you can do this on the Casio or the TI. You can either use the chart or you can use the inverse norm. So second bars, inverse norm is number 3. The area is 0.02. And leave your mean and standard deviation alone. We get a critical value of negative 2.05, just like we did here. Casio, same kind of thing. Mode, down to distributions, number 3.02. Leave those alone, negative 2.05. So either way you do it, you'll still get this. You can also use the chart, entirely up to you. So we rejected the null. Claim was in the alternative, so we support the claim. Next one, let's look at it. Used car dealer says that the mean price of a 2-year-old sedan is less than 19,423. So that. You suspect this claim is incorrect and find that a random sample of 16 similar vehicles has a mean price of this. Assume the population standard deviation is that. Is there enough evidence to support the dealer's claim at alpha equals 0.05? So write down your hypotheses. The mean is less than, that's going to go in the alternative again, 19423. So the null would be greater than or equal to $19,423. Our claim is in the alternative. Write down our key information, 16 vehicles. X bar, because those have a mean of 18,879. And again, tells us the population standard deviation, 750. That makes this a Z test. Again, you could have this exact question, but as a T test. It will be random. And yes, this is what your test score will look like with different numbers and possibly different Z's and T's. So if you fail test 4, it's your own damn fault. And alpha is 0.05. Not talking to you, Taylor. I'm talking about all the people that won't watch this video. Okay, so we got the information. Let's again calculate the test statistic. That's not the test. Yes, it is. Z is X bar minus mu over sigma divided by square root of 16. You could just put a 4 if you want to. I don't care. You don't have to show this step. You just need to give me that test statistic. But if you screw up for some reason and don't write this step, then I won't be able to give you any partial credit. So again, I'm going to type this in. Got a fraction. $750 over square root of 16. And that gives me negative 2.013, or negative 2.9013, sorry. Again, probably only need 2 decimal places, depends on how you're doing it though. I like to go 4 just to be safe, because sometimes your critical values might have 3 decimal places. That's the test statistic. Next, we need to find the critical values. Let's see, it's a left tail, so that means our critical value is going to be negative. We're going to look up 0.05 in the chart. 1.645, if I don't, yeah. So 0.05 is 1.645. Done that one a few times, you probably remember it. And you could use your Casio or TI and do an inverse normal. I believe you'll get 1.456. No, 1.645, same thing. Okay. So there you go, there's that. We've got the critical value, we've got the test statistic. Let's plot it. Draw your curve, sketch it. Here's 0. Here's my my critical value. Shade. Plot my test statistic. And that's negative 2.90. I'll just put negative 2.9 for space reasons. But it's far enough away. You can tell that's in the rejection region, so we are going to reject the null. All right. P-value method tells us to look up the area on this one. It's a left tail, so we're going to look up the area to the left of negative 2.09 or 2.90. If you don't remember how to do that, flow chart's right here, left tail, area to the left. 2.90 is 0.0019. So P equals 0.0019. P is less than alpha. So we're again gonna reject the null. Okay. So that's our initial conclusion. We're rejecting the null. Our final conclusion will be the same as the previous problem. There is enough evidence to support the claim. And then whatever the heck claim is. That the mean price of a 2-year, I cannot spell today, old sedan is less than 19,423. Sure. That's it for number 2. Good so far, Manuel? I'm sure you're fine. All right, let's see what we got going on this Okay, homeowners claim that the mean speed of automobiles traveling on the street is at least the speed limit of 15 miles per hour. So that's my claim right here, at least 15 miles per hour. Random sample of 25 automobiles has a mean speed of 14.5 miles per hour and a standard deviation of 3.9 miles per hour. Is there enough evidence to reject a claim at 0.01? Let's see. So my null and my alternative. Okay, so at least that's greater than or equal to. That's going in my null this time. And it's greater than or equal to 15. That makes my alternative less than. And this is my claim right here. So my claim is in the null this time. So remember, if the claim is in the alternative, we can either support or there's not enough evidence to support. If the claim is in the null, we either reject or fail to reject. Let's find out what we're going to do on this one. N, that's an N, not an R. N is 25. Mean of those 25 is 14.5. And the standard deviation, what kind of standard deviation? A random sample has a mean speed of this and a standard deviation of that. That's S. It doesn't say it's the population standard deviation. That's the sample standard deviation. That's making this a t-test. So that's right there, either S or sigma, whichever one you got tells you what you're using. And we still need that alpha value, 0.01. Okay. So we are going to look over here and find our test statistic for T. It's pretty much the same formula as Z, just with S instead of sigma. So we got a T test going on this one. There it is. So same process. Let me change the color. X bar, oops, for some reason I didn't put 0.5. 14.5 minus move 15, S 3.9 divided by square root of 25. Figure out what that is using the nice little Casio here. Go to mode 1. Fraction bar 14.5 minus 15 over 3.9 over square root of 25. And that gives me a negative 0.641. And on this one, if we look at our chart, it's a T chart this time. Don't use a Z. We're looking at the T. These all have 3 decimal places, so make sure you go to 4, just to make sure you know what you're doing. So to get my critical values now, to get my critical value, I'm going to look up alpha. It's a left tail, which makes it a 1 tail. It's a left tail, which makes it negative. So a 1 tail with an alpha of 0.01. Area 1 tail, 0.01. I'm going to use the second column here. My degrees of freedom, N is 25, N minus 1 would be 24 degrees of freedom. So second column, this row, 2.492. So my critical value is negative 2.492. Okay. we're going to sketch that. Again, mean is in the middle at 0. Terrible drawing, but you get it. Negative 2.492. Area to the left, because it's left tail, that's the critical region. And if we look at our test statistic, it's negative 0.64. That's over here somewhere. So I'll just put T there. The test statistic is right here. It's not in the rejection region. So we're going to fail to reject the null. That's our initial conclusion. Okay. So for the p-value on the t's, remember for the p-value, we're actually going to get a t-interval on t-test, unless you're using a ti, which I'll do that in a second. But to get the p-interval for a t-test, you're going to look at same degrees of freedom. So n is 25, 24 degrees of freedom. But you're going to look up where your test statistic is, 0.6 negative. Well, ignore the negative, 0.64. So 24.64, we're looking at these numbers, they're going down. So it's somewhere over here. If we look at what's going on, the area is getting bigger as we go to the right. So what we can say about the p-value is that it's bigger than 0.10, because as these numbers are going down, these numbers are going up. So all we can say for sure for the t is that p is greater than 0.1. I use 0.1 because our test statistic was to the right. Look at this row. It's, ignore the negative, 0.64. 0.64 is to the right of this. It's going in decreasing order, descending order. So the last alpha value here is 0.1. They're getting bigger, so p is bigger than 0.1. That means p is definitely greater than 0.01, so p is greater than alpha. So again, we're going to fail to reject the null. Now our claim was in the null. We failed to reject the null. So there is not enough evidence to reject the claim. There is not enough evidence to reject the claim that. And who cares, whatever that highlighted part is right there. The mean speed of automobiles traveling on their street is at least the speed limit of 15 miles per hour. Okay, good, done. Question on that one. I will do the t-test on the calculator in just a second. Let me know if you have a question though while I do that. So TI users, pretty similar process. Instead of selecting number 1, you're going to select number 2. Still have statistics. Mu is 15. X bar is 14.5. S is 3.9. N is 25. And again, it's a left tail. I guess I love these left tails. Calculate. And it gives us our test statistic, 0.6410, 0.6410, and our p-value. Now, if you're using a TI, it gives us the actual p-value, 0.2637, or 38. If you're using a chart, you can't get this p-value from the chart. You can't get that accurate. However, we can say that p is greater than 0.1. That's what we established. And if you look at it, 0.26 is definitely greater than 0.1. So yeah, we're not wrong. So TI users, you actually put the p-value 0.2638. And that's definitely bigger than 0.01. So yeah, we're good. Got to reject the null. not enough evidence to reject the claim. That's it for the t-test here. Let's see what we got coming up next. And again, on all of these problems, we're going to find test statistic first. Then we're going to find the critical value, sketch it. Then we're going to find the p-value. And we're going to write our initial conclusion and the final conclusion. By the way, I grabbed these problems directly from possible versions of the final exam, so there's that. If you want to look at these again later, it'll help. Ooh, power. There we go. Company, who cares, says that the mean conductivity of the river is less than 2,147 milligrams per liter. Conductivity is who cares, really. What we do care about is this right here. That's our claim. And we randomly select 41 samples. That's our N. Sample mean, well, it even says sample mean, so yeah, right there. The sample has a mean of 1,742 and a standard deviation of 926. So again, this is the sample's standard deviation. Notice on the previous problem, the population standard deviation is 750. It specifically tells you it's either the population standard deviation or it's talking about the sample's standard deviation. You got to pay attention. Start with our hypotheses. All of them were left tails. Seriously? I got to pick less random things. Hey, Tara, calculate the probability that all 4 of the problems were left tails. Got it yet? So mu is less than 2147. So for our null, it was greater than or equal to 2147. So that right there, our claim is in the alternative. N is 41. X bar is 1742. S is 926. And an alpha value of 0.01 is what we're looking at. Start with the test statistic. Again, we have a t-test because this is S. There's my test statistic right there, the formula for it. X bar minus mu over S over square root of N. And let's see what we got going on this one. We got a fraction. That's fraction at the bottom. And we get negative 2.8005. Okay. So let's see. That's our test statistic. Next is the critical value. Let's see, N is 41, so 40 degrees of freedom. Left tail, so it's going to be negative 0.01. So 0.01 in one tail is again the second column. N is 41, degrees of freedom is 40. Right here, second column, 2.423. Sketch what we got. Here's my critical value. Shade to the left. Sorry that they're all left tails. Now I'm going to plot my test statistic. Negative 2.8. Boom, it's inside of there. We're going to reject the null. Now let me get my p-value. My test statistic is negative 2.8. So it's to the left of 2.7. So it's going to be less than 0.005. So this number right here is 2.7, and they're getting smaller. So we need to get bigger. 2.8 is bigger than 2.7. So it's the left right here somewhere. These numbers are getting smaller as we go to the left. So it's p less than 0.005. So we can definitely say that's less than 0.01. So p is less than alpha. We reject the null. Again, TI users, you can see exactly what the p-value is. Okay, our claim was in the alternative. We rejected the null. We support the claim. There is enough evidence to support the claim that the mean conductivity, whatever, of the river is less than 2147 milligrams per liter. Done. You with me, Taylor? Good to go. That was the last VT practice problem. I believe next we're going to do some P's. Yeah, the honeybee problem. You probably remember this one or not. It was on the quiz there for our P test. A sample of a lot of honeybees. So that's my sample. That's N. My bee colony was tested for mites. This many of that many were found to have mites. Test the claim that less than 6.1% of bees have mites at the 10% significance level. So let's write down what we're hypothesizing here. Seriously, hang on. Okay, next one's not a left tail. 5 out of 6 were left tails. Wow. So H1 is where our claim's at. It's less than 6.1%. So P is less than 0.061. Again, convert it from a percentage, make it nice. P greater than or equal to 0.061 is our null. Claim is in the alternative. So let's write down what we got. N is 2, 3, 4, 7, 3. P hat is going to be this out of that. So this out of the total. We already got P. Alpha is 10%. Let me go ahead and write down what P and Q are. P is right here, 0.061. So Q is 0.939. Remember, they're complements. So 1 minus P gives you Q. Now, if we look, again, we're going to find the test statistic first. Come on. Right here. Test statistic for a proportion. Notice we're not talking about the mean in this problem. It doesn't say anything about mean in here. We're talking about a percentage, a proportion of the bees having mites. So that's how we know to use the P instead of the X bars and the moves. So it's a proportion test. Oh. We've got P hat, we've got P, we got P, we got Q, we got N. All right, let's type it in here. So again, P tests use Z scores. It's a Z here. It's a Z score for the test statistic, it's a Z score for the critical values. So we can calculate this test statistic. P hat minus P over square root, big square root, P times Q. That's P times Q, not P hat times Q hat. Over N. Let's see what we come up with. So clear that out of there. I've got a fraction with a fraction. My internet connection is unstable. Let me know if, well, you won't be able to let me know if I lose you. If I lose you, I'm sorry. 1136 over 23473 minus 0.061 over the square root with a fraction, 0.061 times 0.939, 23473. Make sure this whole thing's in the square root. And we come up with a ridiculously large that ridiculously large test statistic there. So, yeah, that's going to be our test statistic. Negative 8.0685, unless I did something wrong. I'm going to just do 8.685. Let me just type this in the TI, make sure I didn't type something in the calculator wrong here. Should we match stat test? For a P test, we're going to do another A. Oh, no, that's the interval. We're going to do a number 5. So P naught, that's P, 0.061. X, that's the numerator here. If you're given a percentage, you're going to multiply that times N and round to the nearest whole number. N is 23473. It's a left tail, so that's good. And okay, yeah, we didn't screw up typing things in. It's just a ridiculously large test statistic. So that's my test statistic. Now let's find the critical values. I will make sure the test statistics are more reasonable on the test. So they'll be between positive and negative 3. Critical value. Where are we at? We're at critical value. It's a Z, because it's for P test, so it's going to be a Z score. Looking at 0.1 for my alpha value. The left tail, that's a 1 tail. course, you can do inverse norm, or you can look it up on the chart here. We're looking at 0.1. And 0.1 is, let's see, this is closer. It's either 0.1003 or 0.0985. So this is definitely closer. 8, so it's negative 1.28. So 1.28, and then it's a left tail, so make sure that's negative. Sketch it. All right, there's a good spot. Shade to the left. And my test statistic, -8, is way the heck over here. Definitely in the rejection region. So p-values, if you saw it on the TI already, it's 0. So it's really, really small. It's rounded to 0. If we use the chart, it's the area to the left of -8, 0.07 if you really care, but anything lower than -3.50, we use 0.0001. And if we use the TI, it's actually even much more ridiculously small. It's 0. So either way, these are both really tiny. P is going to be less than alpha. So we reject the null. Yeah, sure, that's narrow. Claim was in the alternative, so same old, same old. There is enough evidence to support the claim that less than 6.1% of the bees have mites. That's the conclusion. This is the initial conclusion. We're good to go on that one. Stop me if you have a question. Okay. Last hypothesis test. Gallup poll, we had 16,538 adults, 25.2%. So that's again going to be a P test here. Smoked cigarettes in the past week. These are 1% significance level test claim that 26.3% of adults have smoked the past week. So that's actually a two-tailed test finally. 26.3% smoked, so that's equals. Oops, move that over a little bit. There. No. Stop. So P equals 26.3%, which we don't like percent, so I'm going to change that to 0.263. And that would make our alternative not equal to, which means we finally have a two-tail test and not a left tail. Okie dokie then. N is 16,538. P hat, well, P is that, so P hat is this percentage down here. Ah, crap. No, that's the ones that were surveyed. That's P hat, 0.252. This is a survey that's sample proportion. That's the claims, that's our population proportion. P is 0.263. Do some basic arithmetic. Q is 0.737. Alpha is 0.01, 1%. And now we're going to calculate that test statistic again. So let me do it in blue. Z-score for the test statistic is 0.252 minus 0.263 over square root P times Q right here, 0.263, that's a decimal, times 0.737 over, N is really large here, 16538. That's going to be pretty big, I bet. Let's see. Okay, 0.752 minus 0.263 over square root with a fraction side of it, 263 times 0.737. That's over 16,578. Holy crap. 143. Oh, wow. Somehow, what? No idea what happened there. Okay, whatever. I'm just going to retype it in. 0.252 minus 0.263 over square root with a fraction, 0.263 times 0.737 over 16578. Okay, that's quite a bit more reasonable. I don't know what happened that first time. Negative 3.2170. And I'm going to use the TI just to check it. Make sure I have the right test statistic before I move on. So P 0.263 X. Okay, TI users, this is where I was telling you, we don't know what X is. So we have to take our proportion, 0.252 P hat, times N. That gives us 4167.5, blah. So that means we got to round that up. We cannot have decimals in here. That's got to turn into an 8. Rounds up to 8. Type in these guys. And it is a two-tailed test. That's only going to affect P. It won't affect the test statistic. Negative 3.2056. Close enough. Yeah. Since we do use 0.252 versus whatever the heck that other thing would make it, it's going to be slightly different. And that's perfectly fine. There's an interval of possible answers I accept. There's that. That's our test statistic. Let's get the critical values. And why not use inverse norm? So it's a two-tailed test. Split alpha in half. One positive, one negative. Mode, distribution. Number 3. Instead of 0.01, we're going to do 0.01 divided by 2. Leave those alone. Negative 2.576. So it's a two tails, we also have positive 2.576. We got both of them. Those are our critical values since it's a two tail. Not equal to makes it a two tail. Two critical values. If we sketch it, we're going to see both of our tails shaded. This is, I'll just do negative 2.6, positive 2.6. Shade the right tail, shade the left tail. And if we plot our test statistic, negative 3.2, it's going in here. So it's in the rejection region, so we reject the null. Okay. We can also get the p-value. The area to the left of negative 3.2. Where are we at? Negative 3.22. So we get 0.0006 from the chart. You can also do a normal CDF to calculate your p-values. It's entirely up to you. I'll show you real quick. We should get something slightly different. Number 2. Less than. Okay. We actually have to double that. So let me show you again why we doubled that. What kind of test did we have? We had a two-tailed test. The test statistic was to the left. We calculated the area of the left test statistic and double it. That's what the flow chart tells us to do. So this would be 0.0012. If we use the normal CDF, the lower bound is negative infinity. Again, you can just use a chart that's perfectly fine. Upper bound is our test statistic. Leave those alone. And we get 6.5, but we got it, well, 6.47. Who cares, really? It's going to be a 6 after we have 3 zeros. So 0.0006. That's that 10 to the negative 4th power. Moves our decimal back to the left 4 places. That's what we get right here. Again, we find the area to the left and double it twice the area to the left because it's a two tail. And if we looked at what the TI told us, it was 0.0013. Really close. Either way, P is less than alpha. And we're going to reject the null. Rejected the null. Oh, I didn't write down where my claim was. The claim was in the null. So there is enough evidence to reject the claim that .3% of adults have smoked in the past week. So that's it for hypothesis testing. We've got a correlation coefficient and a linear regression coming up. Easy peasy on these guys. And that's going to be the entire test for review. So again, regardless of which calculator you use, you're just going to type in the information and do whatever it tells you. So it says find the best predicted weight, and this one says what is relationship? So to find the best predicted weight, we first have to see if there is a correlation. If there is a correlation, then we find our regression equation and plug it in. If there's no correlation, we use y-bar. Let's find out. I'll do one on the Casio, one on the TI. I'll do some on the Casio. So we're going to go to, well, let me start over. Mode number 3, number 2. Type in your X's and your Y's. Move. That out of the way. Okay. Back up there. So now I'm going to type in this data. 70, 70.5, 68, 65, 70, 70. Oops. And make sure you don't screw up like I just did there. 70. Oh, how many 70s? 1, 2, 3, 4. 1, 2, 3, 4, and then a 71. And 9 values, let me make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, at least I didn't miss or add one. And then we type in their weights. 117, 119, 105, 115, 119, 127, 113, 123, 115. And they match. So have that data typed in, get out of there. So the first thing I'm going to do is I'm going to go to my regression. So stat number 5. And let me look at what R is. R is pretty low. It's 0.360. So I'm going to go ahead and write down my regression equation. Regression equation, if we need it. If we don't, well, we'll just use y-bar. Let's find out. This is my R. We'll test and see if it's significant in a minute. Right now, let me go ahead and get my A and my B for my regression equation. So that's A. And that's B. So I'm going to write down my regression equation. Are we going to use it? Maybe, maybe not. So whenever we're doing regression equations, we still have to do the correlation coefficient just to see if we can use the regression equation or not to predict the value. So on the Casio, it's A plus BX. On the TI, it's AX plus B. Pay attention to whatever your calculator says. So in this case, we're going to do Y equals 31.841. I'm just going to round it. Plus 1.227x. I am not going to make you do these by hand on test 4. I'm going to give you the data. I'm just going to give it to you. I'm not sure how they're going to do it on the final. If they have stats instead of data on the final, then we'll go over that when we get to it. But on the test for Friday, I'm just going to give you 2 sets of data. One you're going to do a regression, one you're going to do the correlation. To do a regression, you also have to look at the correlation. Now let's see. We have 9 pairs of numbers, so n is 9. And our R value we got was 0.36. I'm thinking that's no. Oh, wrong way. So look over here on this correlation chart. It's on page 3. That's the front of the second page. So n was 9. Yeah. So 0.666 would be the very minimum R correlation coefficient that would allow us to use that regression equation. That ain't nowhere near 666. So we're not going to use this. Instead, we're going to use Y bar. I'm going to go to my variables, maybe. Yeah, number 5. Y bar is 117. So the best predicted weight would be 117. If the correlation coefficient was greater than 0.666, we'd plug in 72 into this equation, see what it popped out with. But that ain't good enough. So we just use the average of the weight, Y bar. Okay. So question on that one. Seems like a no. Okay. Let's look at this one. One classic application of correlation involves association between temperature and number of times a cricket chirps in a minute. Okay. Somebody was bored counting cricket chirps. Is there sufficient evidence to conclude that there's a relationship between the number of chirps in 1 minute and the temperature? So I'll do this one on the TI, just because I did the other one on the Casio. Process is identical for both these things. Just depends on what you're trying to deal with. On the previous one, we had a regression equation. This one, we're just looking at the correlation coefficient, nothing more. So let's see. Grab my TI. Stat, edit, clear out my list, go to the top, clear, enter, top, clear, enter. So make sure you type your X's in list 1, your Y's in list 2. These are my X's on the top row, Y's on the bottom row. 882, 1188, 1104, 864, 1200. Oops. There we go. 1032, 960, and 900. What? Okay, no. 960, let me just do it this way. And 900. Okay, so that's 8 values. 1, 2, 3, 4, 5, 6, 7, 8. Good. Now type in the corresponding temperatures. 69.7, 93.3, 84.3, 76.3, 88.6, 82.6, 71.6, 79.6. A lot of 0.6s. And those match in dimension, so hopefully we didn't screw up typing anything. All right, now we need to run the regression equation. And we're going to go to stat, calc, number 4. And what you will actually have, it'll instantly pop up with this, without that on there. You'll see this on your screen, just hit enter. Done. If you don't have R, then you haven't watched any of the videos, go back and watch them. So yeah, it gives us R, and again, if it doesn't, go watch the videos, the previous ones, all of them. So we have our regression equation here, so if we needed a regression equation, there it is. Again, it's Y equals AX plus B for the TIs, but that's not what we care about. We care about R, 0.874. We're going to round to 3 decimal places, 0.874. And we're going to compare that. We don't have an alpha value, so let's just see. Wait, how many data values do you have? 1, 2, 3, 4, 5, 6, 7, 8. We have 8 pairs of data. Okay, so at alpha is 0.05, we just need 0.707. So it's good for 0.05 significance. For 0.01, it's 8.34. Still good. So yeah, there's a significant correlation between the temperature and the number of chirps for a cricket. And whoever the heck was bored enough to count those cricket chirps, I don't know, maybe you're in quarantine. So yes, there is a correlation between the number of chirps in 1 minute and the temperature. And let's examine this correlation. It's just asking if there is one. That's all I'm going to ask. But let's look at what kind of relationship it is. It's a positive R. So again, a positive R indicates a direct relationship. As one goes up, the other goes up. If it's a negative relationship, as one goes up, the other goes down. The closer R is to 1, the stronger that relationship is, and that is the absolute value of R I'm talking about. So an R of 1 or negative 1 are perfect correlation. R of 0 is absolutely no correlation whatsoever. All right, I do believe that's all, folks, or folk in this case. So, any questions? Guess not. All right, guys, that wraps it up for test 4 review. I'm going to post it on YouTube, and tomorrow, if you have any additional questions, you can ask them. I expect you've already watched the other videos, so I'm not going to repeat myself. All right, guys, have a good day.